Y'all, Darren Berry Jr. here, back for some more physics. And as promised, we'll be doing some graduate level work today. So you can see the image on the left, that's what we'll be working with, the chaotic pendulum or the double pendulum. It's chaotic, meaning that a small difference in the initial conditions makes a very big result. So a small perturbation, large change. So with a regular pendulum, if we pull it back in a small amount and let it swing, it just swings back and forth. If we do the same thing again, but put it a slightly different distance, very, very small distance different than the first time, it'll still operate the same way, maybe a little bit smaller, a little bit larger amplitude. But with a chaotic pendulum, a very small difference in starting position makes drastically different results. So you can just look online and search a chaotic pendulum or a double pendulum, and you'll be able to see how wildly it moves depending on, over the course of multiple different hours of the same pendulum running. So we'll go ahead and get the equations of motion for this problem with the Lagrangian method, which may be the only method we can use to do that. So what I'll do, I'm going to make my own drawing. And we'll go from there. If you haven't already, make sure you like, subscribe. Let me know if you have any questions along the way. And I am available for tutoring. If you want to get ahead on the next semester, or I should have some time next semester as well. We have our two pendulums. Maybe I'll make the angles a bit easier to see. Right, so we have these two pendulums. I shall use the same naming convention in the illustration listed. And we have a vertical here. Right? So this is the setup that we're looking at. We have our two masses, M1 and M2. We have the two, we'll consider massless beams that are connecting them, one to the base, one to the first mass. Um, we have the angles between the vertical and the pendulum for each one. And we're going to use the Lagrangian method of solving the problem. So the Lagrangian method basically takes a function of generalized coordinates, and it is basically the kinetic energy minus the potential energy. So to get the equations of motion, rather than trying to figure out the arrangement in a Newtonian sense, we can simply figure out the energy of the system, the kinetic energy and the potential energy, subtract the potential energy from the kinetic energy, and then we can plug that result into the Euler-Lagrange equation. And we plug this in, and that'll be our L there. We can actually output the equations of motion just from taking these steps. So what we need to do now is figure out what the kinetic energy and potential energy is for the system, if you can apply the Lagrangian formulation. Right? So we know that kinetic energy is 1/2 mv squared, and we're going to have to sum up the kinetic energies for each of the masses. So we can have 1/2, this will be I, 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Looking at this, we can simplify the problem a bit by finding some generalized coordinates, which is what Q is. So that'll allow us to put this kinetic energy and potential energy in terms that is more simple for us to resolve. So what we can do is utilize the degrees of freedom and see if we can reduce those somewhat. So the way these problems work is we have 3 degrees of freedom per problem, since we're in 3-dimensional space, not including time as a dimension, per particle. So n is the number of particles. And then F are the equations of constraint, the things that limit the system in a certain way. So we can consider this pendulum to be a plane pendulum, meaning that the pendulum does not go sideways, it just moves within the plane of the page back and forth. Therefore, we can say that there's only an x and y, so z equals 0 is one limit or constraint on the situation. And z1 equals 0 and z2 equals 0 for each mass. We can also say that the L's are constant. Right? We can say that L is constant for L1 and L2 is constant. So we have 4 things that don't change, that limit the movement of these masses in 3D space. It's always going to be in the plane of the page. So neither of the masses are going to, from all 3 dimensions, just 2. And however much M2 moves, it can still only move limited by where M1 moves, since they're connected. And however much M1 moves, it can only move so much because it's connected to the bar at the top. So those are limits. The fact that L1 and L2 are connected and unmoving. So we can say 3 2 minus 4 is 6 minus 4 is 2. So we have 2 modified degrees of freedom that we can utilize to simplify this problem. It is easier to see what those degrees of freedom will be, theta 1 and theta 2. So that means that these Q's, these QI's, are going to be theta 1 and theta 2. So I can say my L is going to be theta 1, theta 2, theta 1 dot, and theta 2 dot. Those would be the generalized coordinates that I'll be able to utilize for the Lagrangian. So all we have to do now is take the x and y coordinates that we have here and put those in terms of theta 1 and theta 2. And you can use that with trigonometric functions. So we can start with x1 equals L1 cosine theta 1, and y1 equals L1 sine theta 1. So I'm going to make sure I put the proper ones on each one. So actually, looking at how I chose my angle, I might have chosen the top angle when I did this one before. So I don't mind doing it the reverse way. Yeah, I did it the reverse way before. So the way I have it set up here, actually, and I'll just do it the way I wrote it here. We actually have that x is sine of theta 1, and y is cosine theta 1. So you can see how sine of theta is opposite over adjacent. This is x, this is y. So sine of theta is x over y, x over L, the opposite. So x is L sine theta 1, and we have that there. And we can go ahead and get the derivative of x. What we did there was the chain rule as a time derivative. So we have the L is constant, but cosine is a function of theta, which is a function of t. So you have L1 cosine theta 1. Then you have to take the derivative of the argument for the chain rule. So you have theta 1 dot. Same thing with that one. So now we have our derivatives of our two s components. Now we need to get the y component. Now it gets a bit more complicated with the y. The 2's, because we can say that x2, meaning how far the second mass moves in the x direction, is this. So if the origin is here, in our coordinate system. So that's x equals 0. Then x2 is going to be that entire distance, including them both. So x2 equals x1 plus, so this is still x1, y1. This is x1. We'll call this x2 prime. So x2 is x1 plus x2 prime. And we can see that x2 prime, we can say sine of theta 2 is x2 prime over L2. So x2 prime is L2 sine of theta 2. Check my notes, make sure I didn't make any errors. Everything looks good. So then we have to take the time derivative of this one. Should be a cosine. So we have that. Everything seems good. And we have the same thing with y1, excuse me, y2. Let's check to confirm. We have y2, it's all the way down here. That's still our y1 there. This is our y2 prime. So y2 equals y1 plus y2 prime, which equals L1 cosine theta 1 plus L2 cosine theta 2, y dot 2 equals negative L1 sine theta 1 theta dot 1 minus L2 sine theta 2 theta dot 2. So that's going to be negative theta 1 dot L1 sine theta 1 minus theta 2 dot L2 sine theta 2. So now we have the components that we need for velocity, because this is 1/2 m1 x1 dot squared plus y1 dot squared plus 1/2, and it's the same thing for the 2 version. So we'll go ahead and plug that in. We have t equals 1/2 m1 m2 x2 dot square plus 1 m2 y2 dot square. It looks good. So to plug these in, I'll just copy these down. And I'll go ahead and simplify this equation. Straightforward enough. The next line we have a foil. That's that one. We have the last foil. Yeah, I've skipped the line. Let me see here. First line, second line. I think that is good. After all, we'll see in a bit. Wait, I did skip a line. I see it now. Still cosine. Check my notes, make sure I didn't miss anywhere else. So I'm doing this one the reverse of when I did it the last time, so not so familiar, but we'll work it out. Let's see what we have. So for the first part, we have 1/2 m theta 1 squared L1 squared. And that cancels out the cosines. And we have plus 1/2 2 theta 1 dot squared. The cosines and sines cancel out here. We have plus 1/2 m2 theta 2 dot squared L2 squared. And the cosines here cancel out. We have plus 2 theta 1 dot theta 2 dot L1 L2. And do we have uh, cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. And it's different from what I had before because of the changes I said, but it's generally consistent. I think we are good. I got my 1/2 m2 here. I gotta put a parentheses in the back, so that's good. So let's see what we have here. So this is where I left off my M2. All right, there we go. So I think everything is right now. So what we can do here is actually utilize some identities. So trigonometric identities usually crop up in these things. We have cosine theta 1, cosine theta 2 equals cosine theta 1 plus theta 2 plus cosine theta 1 minus theta 2. And then for this one, we have sine theta 1 sine theta 2 equals 1 half cosine theta 1 minus theta 2 minus cosine theta 1 plus theta 2. So we call this A and we call this B. And we see up there it's A minus B. So that's going to be 1 half cosine theta 1 minus theta 2 plus 1 half cosine theta 1 minus theta 2. Cosine theta 1 minus theta 2 plus 1 half cosine theta 1 plus theta 2. But it should be canceling the cross. Let me see what if I made an error somewhere. But yes, it will be subtracted. So that means that this will be 0. Now it's the top minus the one over there, and that will be 2. So it ends up being 1 half cosine theta 1 plus theta 2 plus 1 half cosine theta 1 plus theta 2. So it ends up cosine theta 1 plus theta 2. So going back to our original problem. So this is, some identity work. We have uh, we have theta dot squared squared plus 1 half theta 1. Actually, we'll go 1 half 2 theta 1 dot squared L1 squared plus theta 2 dot squared L2 squared plus M2 theta 1 dot theta 2 dot L1 L2. And then we have cosine theta 1 plus theta 2. Right? See what we have here. Consolidated it slightly differently than before. Maybe we should do it the same way as before. So here I consolidate based upon the mass. And I should consolidate based upon the generalized coordinates to make the later parts easier. So looking at the generalized coordinates, we have theta 1 squared for the first two. We have 1/2 theta 1 squared L1 squared M1 plus M2 for the first two. And we have plus 1/2 M2 theta 2 dot squared L2 squared. So the theta 2 is separate. Should be a dot. And we have the last one plus 1/2 plus just another 1/2 for that one plus M2 theta 1 dot theta 2 dot L1 L2. And then we have cosine theta 1 plus 2. And I think that's it. So there's still a slight variation in the identity. A different one would have canceled, but I use the other way of assigning my angles. Everything else is the same. We have theta 1 carries both masses. So when theta 1 moves, we can see that both masses move. Theta 2 carries only the second mass. So that's why we have here the first angle has both M1 and M2. The second angle has only M2. But then there's sort of a cross uh, term for both masses. And then notice that's only on M2 because M2 does carry both, move according to either angle separately as well. So both masses move according to theta 1, but each angle separately moves theta 2. And then theta 2 could just move by itself if the first mass is stationary. So these equations account for that for the kinetic energy, right? Now we can look at the potential energy. So the potential energy is generally mgh, the mass times gravity times the height. And what we'll do is assign this as the potential is 0. And potential can be negative, depending on what we define 0 to be. It's interesting thing about potential because, if I hold a rock above the ground, it has a certain amount of potential when it falls. But I could also hold that rock above the ground on the top of a building. So do we count the ground on the other side of the edge of the building as 0, or do we count the roof of the building as 0? So, whichever one we count, if we drop it on the roof, it'll still fall the same distance. So the calculation will be different depending on the different axes we set, but the overall energy change is the same. So what we'll do is count that as being 0, which means that the H is negative. So we can say that so potential for each one. So mass 1, H, is going to be the Y component. Imagine it should be like this, nice and straightforward. Let's check and see. Seems to be it. The only thing I missed was, since I'm counting the top as being 0, the both of these would be negative. So if y1 is 0, then the potential energy is 0. But if y1 is L1, the potential energy will be mgl1, which would be positive, but we need it to be negative because it's going down. So there's a negative mgy1. I guess it's possible that we can just call it mgy1 and consider the negative when we actually put in the actual value, like -2 for y or whatever. But I think it's fine to include the negative now as well. And we can consider putting in the magnitude for the y value. We'll do it like that, because that's the way I did it before. Even though I am sort of curious how the problem will come out differently if I change that, but I don't want to change too much. So we have the same things we can plug in from earlier. That's right. If I put the negative on the earlier, I'll put it in twice. Put the negative on there twice. Right? So I have negative mg the derivative one. And welcome who's joined. Let me know if you have any questions or comments. We're doing a double pendulum, chaotic motion with the Lagrangian method. M's. My H's with my subnumbers, but not my M's. Minus M2 V Y1 plus Y1 prime. At here. Simple enough. So MGH. I can also simplify this according to where the angles are. So we have negative M1 G L1 cosine theta 1 minus M2 G L1 cosine theta 1 minus M2 G L2 cosine theta 2. So that means we have negative M1 G L1 plus M2 G L1 cosine theta 1 minus M2 G L2 cosine theta 2. I've extracted the GL1 as well. But the right idea, get the angles together. We have that. Right. Now we can go ahead and make our Lagrangian, which is going to be our kinetic energy. Now we have minus V. Be a plus there, and a plus there. Right, so we have that. So this is our very long, complicated Lagrangian, but it's apparently simpler than trying to do the problem the long way, which would really be with um, Newtonian mechanics. Right. So now all we have to do is plug this in to the equation that I had mentioned earlier, the Euler-Lagrange equation. Except that these q's will be the generalized coordinates that we found, which were theta 1 and theta 2. So if I was to start with theta 1, we have d dt partial L over partial theta 1 dot minus partial L over partial theta 1 equals 0. So I'll do partial L over partial theta dot 1. That's our Lagrangian there. So I'm going to find all the theta 1s, theta 1 dots, and take that derivative. So we have theta 1 dot L1 squared M1 plus M2 plus M2 theta 2 dot L1 L2 cosine theta 1 plus theta 2. And we have to take the time derivative of that, the full time derivative of partial L over partial theta 1 dot. So we have, and let me take my plug out so I can get some better space. We have, so this is going to be a chain rule. We have theta 1 double dot L1 squared M1 plus M2. Then we have plus M2 theta 2 double dot L1 L2 cosine theta 1 plus theta 2. Now it's a derivative on the theta dot. Now I have to take the derivative on the cosine. So that's m2 theta 2 dot L1 L2 sine theta 1 plus theta 2. And the derivative on the cosine will make that negative. And then I got to take the derivative of the argument, which is going to be theta 1 dot. So I'll go ahead and plug the theta 1 dot in the front. That should be that. And then we have partial L over partial theta 1 equals, and again, I find all the different instances of this theta 1 dot to take the derivative of. So we have two of those. So we have negative m2 theta 1 dot theta 2 dot L1 L2 sine theta 1 plus theta 2. And then we have to take the derivative of the inside, which ends up being just 1. So we could leave that the way it is. And then we have plus m1 plus m2 g L1 sine theta 1. Derivative to the sine makes that negative, and the derivative of the inside would just be 1. Now we can plug that in, and we have this and this. So what I have to do is subtract those according to the equation up there. And I'll go ahead and copy it to make sure it's nice and clear. Put it in the actual form. We have the equation this. There's going to be plus this. Subtracting it already has a negative. And plus this. And we're done. Right. So, and it all equals 0. This in just a little bit. So that's our first equation of motion. And we check and see how it differs from when I did it the other way. I might have left off one term. Let me see here. See the term I left off. Left off one of the cosines. I'm also going to minus m2 theta 2 dot squared L1 L2 cosine theta 1 plus theta 2. So that overlook the fact that both the theta 1 and the theta 2 dot are functions of t. So even though I'm focusing on the theta 1 1, I have to take the derivative of both. So now I have all the terms I need. And this cancels, which means that this one cancels, or it's not there anymore. And now we have the proper equation of motion. We'll check one more time. We have another term. Interesting. Doing it this way, it looks like we go through these one more time. So the theta 1 dot, theta 1 dot here, or theta 1 dot there. So I have just bringing a 2 down for that one. Theta 1 dot L2 M1 plus M2. That case takes care of that one. And then I have the theta 1 dot just disappears. The theta 1, that's the same. And I have the time derivative of that. So I have theta 1 double dot, focusing on the first one, and nothing else changes. And I have M2 theta 2 double dot, nothing else changes. Then we have negative M2 theta 2 dot L1 L2 sine theta 1 plus theta 2, and theta 1 dot, the first one. And then we have the same thing for the second one. Oh, for the second one, minus M2 theta 2 dot squared L1 L2 cosine. And that seems to be good. Then we have the partial of theta 1. These two, so maybe I dropped off a term here. Let's see. We have negative M2 theta 1 dot theta 2 dot L1 L2 sine theta. And the derivative of that is just 1. And then we have minus M1 plus M2 GL sine theta 1. This cancels right off the bat. And we see that when we subtract these two things, this stays. But it looks like these two things cancel. this one and that one. And then we're left with this one that stays. So I didn't do any issues with algebra somewhere. This is what I have for the first equation. It is slightly different from the last one I did it. So I wonder if well, it's more than slightly different. I have an extra two terms the first way. But I did swap up my angles, so I could have thrown everything off and made it different. But that's a process, though, either way. So I might have messed up in some algebra somewhere. And what you would do is do the same process with theta 2. Take the Euler-Lagrange equation and instead do that same process for theta 2. And you'll be able to get a second equation of motion for the theta 2 variable. So there you have it. So we did the complex chaotic double pendulum with the Lagrangian method. Started with making out the diagram, marking the angles, the lengths, solve for the kinetic energy and potential energy, plug that in as made that a Lagrangian by T minus V, plug it into the Euler-Lagrange equation and got the equation of motion. And if you do this yourself, just make sure you check for any algebra mistakes. I may have made an algebra thing somewhere. But other than that, you're good. So I'll be back next week sometime, I'm sure. Like, subscribe if you haven't already. Let me know if you have any questions before I leave. I'm about to pop out in a second. And what I'll do next week, I shall see. The last week of class, well, it's past. I'm on my final exams right now. So my last exam is Tuesday. So we may have a new topic next Saturday. So we'll see how it goes. Let me know if you have any topics you're interested in. Let me know, as long as it's math, physics, or astronomy. And you go to my site there, darrellebrewerjr.com. Let me know if you're interested in tutoring. And it's of note that I'll be doing an outreach next week debating a flat earther. I haven't done that in a while. I got sort of fed up with them. But been interested in having a public speaking event again. So I'll do that next week and sort of make it one of my sort of official graduate outreach things to talk about science. I'll see how it goes. It'll be on Modern Day Debate. I'll post the link sometime soon, I'm sure. And y'all can let me know what y'all think about that. So I'll see y'all next time. I don't see any questions popping up. Y'all have a good one.